So this video is about very long instruction word computers, or VLIWs, and we're going to compare that design point to the out-of-order superscalar implementations that we've discussed earlier. Let's first take a look again at what the superscalar out-of-order implementation would look like. So we have 4 parallel pipelines here. So we can start 4 instructions every cycle, and so we can read from the register file. We can read, all the 4 pipelines can read in this design here at the same time. Before the execution stage, we have the reservation station, where instructions can sit and wait if they have read after write dependence. And we can complete the instructions out of order and put them in the reorder buffer, and then we retire them in order. So they will come to the right pipeline stage in order, and here I sort of implemented that as if we could retire 4 instructions per cycle. There is not necessarily always a match between the width of all these front end as well as execution unit, as well as how many instructions you can retire, but in principle this is how a superscalar would look. Then of course we know that we have the cache hierarchy and all the goodness and badness that comes with that beyond the complexity you see in the superscalar. Important thing here is in the superscalar is that we have what I've called here an issue logic. So this is a piece of logic that looks at a sequential instruction stream and figures out which of these instructions we can issue in parallel. And then we have lots of hardware that figures out what kind of data dependencies we have and figure out when we can actually start working actively on instructions. And then we have a piece of hardware that puts Humpty Dumpty together again and makes sure that we do retire the instructions in order. So quite a lot of hardware that detects the parallelism. Actually, the hardware detects the instruction level parallelism, which instructions can we work on in order, and reorders the execution in such a way that we can maximize the number of instructions we are working on in order. So one of the limitations here with the superscalar execution is that we still have a limited number of execution units, and sometimes we find lots of instruction level parallelism for a short basic block. So let's say we find a basic block and we can fire 8 instructions at the same time, while the limited amount of functional units or the limited amounts of parallel pipelines we have in the design still will limit the throughput we can get from that execution. Still, even though we have a limited number of parallel pipelines, the decoding complexity increases a lot, and all these extra hardware overheads grows drastically with the number of parallel pipelines we have. So it's not as easy to just implement more pipelines to up the amount of ILP you can explore. And solving all these data dependencies and control dependencies and so on more is very costly, especially in terms of energy in a superscalar out-of-order processor. So it would have been better with a single issue processor from an energy point of view, but we also want performance somehow. So what we're going to discuss here is a new design point called VLIW. Well, it's not that new. This was a research topic of the 80s and 90s. And you can view this as a very simple superscalar design where we throw away all the out-of-order crazy stuff, and instead we rely on the compiler, and we trust that the compiler and not the hardware will find enough instructional level parallelism for us. And since we make the hardware simpler without we're not introducing the out-of-orderness, that means that we potentially could have more parallel pipelines for the same cost, and or we could run these pipelines at a higher frequency. So this is what a such an VLIW architecture would look like. In this example I have the same width, but typically you're thinking of VLIWs as having even wider pipelines. So maybe think of this as 6 ways or 8 ways parallel pipelines, where each pipeline just looks like a normal in-order pipeline. So no out of order crazy stuff. So then in each with the read pipeline stage, you would just simply read from the register file. In the write pipeline stage, you will write to the register file, but there are no reorder buffers, there are no reservation stations. And then you rely on the compiler to put together bundles of instructions. So these are the instructions that the compiler has generated, where the compiler says, you know, on this cycle, the first cycle, you can issue a pink instruction, a green instruction, a brown instruction, and a gray instruction. So it's been statically decided by the compiler that it's okay to do so. You can work on those in parallel. And the compiler has also figured out that if you execute these bundles of parallel instructions in exactly this sequence, there will be no read after write dependencies. There will be no write after write dependencies or write after read dependencies. They will hurt you. So that's why you can make this hardware so much simpler. You don't have to detect reordering. You don't have to detect all these read after write dependencies. It's all up to the compiler to do that. So simpler hardware, potentially wider hardware, so we can have more parallel pipelines, and potentially also you can clock it faster, because simpler pipeline you can potentially run faster. So here's an example of how you would schedule exactly the same example we tried to schedule before, where this example of adding the constant 10 to all the elements of a vector. And here we schedule the instructions for a 5-way Vliw, where we have 2 pipelines that can handle memory operations. We have 2 pipelines that can handle floating point operations, and we have 1 pipeline that can handle integer operations as well as branches. And you see what instructions we issue in parallel, and you can quickly figure out that we have, first of all, we have unrolled the loop 7 times here, because we actually schedule 7 load operations here with different kind of offsets into the vector. And so we have all the loads issued up here as a chunk, and then we have a chunk of adds issued here, and of course we also have 7 adds, and then when it's safe to do so, we schedule the corresponding store doubles out here. And looking at this, and then of course we have the integer pipeline, and the integer pipeline is not doing anything useful until at the very end here, when it's time to subtract, in this example, 48 from the integer register R1, and then figure out whether we're going to branch or not. So looking at this, you can see the most common instruction executed here is actually going to be the nope, because there are so many places here where we cannot use all the parallel pipelines, because the compiler could not find any better way of scheduling these instructions, in spite of the fact that we do have unrolled the loop 7 times. There are still lots of unused slots here in this. And just to be very clear about the very long instruction word computer, where that comes from. So in this architecture, the first word or the first instruction word that's executed contains all these 5 instructions here. So the first instruction word, all the instruction words contain 5 instructions that's going to be executed, where 3 of them is a no-op. And actually there is not a single cycle here where we manage to make use of all the functional units in parallel. Here we use 4 out of 5. Down here we're using just 3 out of 5. So it's not that good usage of the execution units, but in terms of number of cycles, we're doing fairly well. We are actually completing 7 iterations of that loop in just 9 cycles. So this is once more a new world record of how fast you can execute. However, there is some deficiencies. We can really see that with the compiler, even with this kind of unrolling, and that is one of the drawbacks of Vliw. It's really difficult to find enough parallelism, instruction level parallelism. So if you have n functional units and you have k dependent pipeline stages, you really need to find n times k independent instructions here to avoid the stalls. And well, you saw that in the previous example, unrolling 7 times was not sufficient for doing that. Also, you cannot rely on some kind of dynamic optimizations. For a pure VLIW implementations, you should not have any branch predictions because you want simple hardware, and you certainly do not have any out-of-order stuff that can compensate for situations where the compiler couldn't find enough instruction level parallelism and reorder the instructions. So how much instruction level parallelism can the compiler really find? Well, that's a $1 billion question for the people that have tried to build commercial VLIW implementations. Another drawback here is that you don't have any binary code compatibility, because the compiler will produce a bundle. In the previous example, it was a bundle of 5 instructions that can be issued at the same time. And if you can't find any useful work, you will simply issue a no-op operation. And then in the next generation, maybe you decided to make a 6-way VLIW pipeline implementation. That means that the first code that only has a bundle of 5 is not compatible with the new implementation with a width of 6. And that is a problem you don't have in the Superscalar. In the Superscalar world, the Superscalar executes actually sequential code. So the code itself, the compiler may not even know how many parallel pipelines there are. It's a sequential stream of instructions, and the hardware figures out how to utilize all the many pipelines. Where here the compiler in the binary representation has to tell exactly how to use the parallel pipelines. Code size is also a problem. So as you saw in the previous example, the most common operation was a no-op. So you're going to have lots of the binary code is just going to contain no-op operation and tell the hardware, please don't do anything, Mr. Hardware, and that is not very efficient. But on the positive side is much simpler hardware. So it takes a shorter time to develop this hardware because it's simpler compared with the 2-Mazzullo algorithm, and it can be run at higher frequency. And what I didn't put in here, probably should have done, is that you can potentially have more parallel pipelines for the same cost as fewer parallel pipelines in the out-of-order implementation. So clearly there are pros and cons. So we're going to do a couple of questions about VLIW's superscalars and out-of-orders. And what I'm going to ask you in this first one, I ask which statement describes a VLIW best. Either is it a simple hardware relying on the compiler to find ILP parallelism, or is it that we have dynamic register renaming to remove some write after write after read dependencies, or is it that we have complex hardware that executes instructions from a sequential stream of instructions in parallel? So it's the first one. It's the simple hardware relying on compilers to find ILP. Asking same question, but instead regarding to 2-Mazzullo's out-of-order pipeline. So which of this statement describes it best? So I would say it's the second one, the dynamic register renaming. And then we ask the same question about just superscalar pipeline implementations. No surprise that the last one is the true statement. It's complex hardware executing instructions from sequential stream of instructions in parallel. So we work on lots of instructions in parallel, but it's not because the compiler told us so, it's because the hardware itself figured out that these are instructions I can work on in parallel.